gas laws. Now in this chapter we shall understand the relationship between the volume, pressure and temperature of gases. But before we look at the laws governing this, let us first remind ourselves the properties of gases. Unlike solids and liquids, gases do not have a definite volume. Gas molecules move in free random motion and therefore can fill any space available. The forces of attraction between molecules are very weak and thus the molecules are far apart, so gases are compressible. Because of this random motion, the molecules collide with each other and also with the walls of the vessels in which they are contained. The collision with the walls of the containers is what causes pressure. So you can increase the pressure of a gas in two ways. One, increase the amount of gas, which will increase the number of molecules colliding per unit time. Or you can increase the temperature, which will increase the kinetic energy of molecules, making them move faster. This will in turn increase the number of collisions per unit time. So the first law, Boyle's law. Boyle's law studies the relationship between pressure and volume of a gas at constant temperature. In this demonstration, we have placed a balloon in an airtight jar. When we suck the air out of the jar, the volume of the balloon is seen to increase. By sucking out air from the jar, what we are doing is reducing the pressure around the balloon, and consequently, the volume increases in an effort by the balloon to equalize this pressure. When we return air into the jar, the balloon decreases in volume. A simpler way to think about this law is compressing air in a vessel. By compressing, what we are doing is increasing pressure and consequently the volume decreases. Notice in this animation that the mass of the gas is fixed as is temperature. Boyle's law states that the volume of a fixed mass of a gas is inversely proportional to pressure, provided the temperature is kept constant. If you plot a graph of volume against pressure, it will appear as per the animation. To obtain a linear curve, we plot P against 1 over V or V against 1 over P. And so according to Boyle's law, the pressure and volume are inversely proportional. If you keep anything else constant, then when the pressure goes up, the volume goes down. And the reverse is also true. If you exert pressure on a gas, you can compress it, you make it take up less space. Imagine a hard container that measures how many times gas particles bang against the walls. The higher the number of times, the higher the pressure on the container. If you make the container smaller, you compress the gas. The particles bang on the wall more times per second. So that means higher pressure. If you keep the number of particles constant but make the size of the container bigger, there will be fewer collisions per second. That registers as lower pressure. Robert Boyle stated the relationship between pressure and volume as a gas law. Boyle's law says that for a given mass of a gas at constant temperature, pressure and volume are inversely proportional. P is inversely proportional to 1 over V. Mathematically, P is equal to K over V, where P is the pressure, V is volume, and K is a proportionality constant. We can rearrange this equation so that it reads PV is equal to K, or the product of pressure and volume is a constant, K. Now, very so often, Boyle's law is used to compare two different situations, a before and an after. In that case, we can say P1V1 is equal to K and P2V2 is also equal to K. Combining these two, we shall have P1V1 is equal to P2V2. Let's take an example. A tire with a volume of 11.41 liters reads 44 psi, that is pounds per square inch, on the tire gauge. What is the new tire pressure if you compress it and its new volume is 10.6 liters? Solution: we write Boyle's law and substitute in what we know. This is a before and after situation. So P1V1 is equal to P2V2. 44 psi times 11.41 liters is equal to P2 times 10.6 liters. Solve for P, we divide both sides by 10.6 liters. So 44 psi times 11.41 liters over 10.6 liters is equal to P2. P2 is equal to 47.36 psi. Notice there are two significant figures in the measurement 44 psi. So we round off our answer to two significant figures, 47 psi. Another example, a syringe has a volume of 10.0 centimeters cubed. The pressure is 1 atmosphere. If you plug the end so that no gas can escape and push the plunger down, what must the final volume be to change the pressure to 3.5 atmospheres? P1V1 is equal to P2V2. 1.0 atmospheres times 10.0 centimeters cubed is equal to 3.5 atmospheres times V2. Solve for V2, divide both sides by 3.5 atmospheres. 1.0 atmospheres times 10.0 centimeters cubed over 3.5 equal to V2. V2 is equal to 2.9 centimeters cubed. Second law, Charles' law. Charles' law deals with the relationship between temperature and volume of a gas at fixed pressure. Consider an inflated balloon at room temperature. When liquid nitrogen at negative 200 degrees Celsius is poured on its surface, it cools the air inside the balloon, which consequently decreases in volume. But as the balloon warms up to room temperature, it reinflates as it gains the volume it had at room temperature. So there is a direct relationship between temperature and volume of a gas. High temperature leads to high volume and vice versa. This is the basis of Charles' law, which states that the volume of a fixed mass of a gas is directly proportional to temperature, provided pressure is kept constant. A graph of volume against temperature is a straight line. The graph is linear and suggests that volume is zero at negative 273 degrees Celsius when extrapolated. In reality, a gas should have condensed into liquid before reaching this temperature. A gas that is theoretically zero at negative 273 degrees Celsius or 0 Kelvin is called an ideal gas. This temperature is called the absolute zero. Absolute temperature scale is given in Kelvin. On the Kelvin scale, negative 200 degrees Celsius is equal to 0 Kelvin. Thus, to convert degrees Celsius to Kelvin, we add 273. And so according to Charles' law, for a gas, temperature and volume are directly proportional. Keeping everything constant, as the temperature of the gas goes up, its volume goes up. As the temperature goes down, the volume goes down. If we heat up a gas, it expands. The gas particles move faster and take up more space. Imagine a balloon that expands when gas particles bang against the sides. By expanding, that keeps the pressure constant. The faster the particles will move, the more they will push on the walls, expanding it. If on the other hand you cool the balloon down, you put it into ice, that slows down the gas particles. So the balloon will contract. Jacques Charles is credited with this gas law. Although he never published it, he may have been way too busy riding on hot air balloons. A colleague, Joseph Gay-Lussac, published it and very honorably gave credit to Charles. Charles' law says that for a given amount of gas at fixed pressure, volume and temperature are directly proportional. V is directly proportional to T. Mathematically, V is equal to kT, where V is the volume, T is the temperature, and K is the proportionality constant. We can rearrange this equation so that it reads V over T is equal to K, or the ratio of volume to temperature is a constant, K. Very often, Charles' law is used to compare two situations, a before and an after. In this case, we can say V1 over T1 is equal to K and V2 over T2 is equal to K. So you can write Charles' law as V1 over T1 is equal to V2 over T2. An example: a hot air balloon has a volume of 2,800 cubic meters at 99 Celsius degrees. What is the volume if air cools to 80 degrees Celsius? Write Charles' law in a before and after situation. V1 over T1 is equal to V2 over T2. Substitute in what we know. Remember to convert temperature to Kelvin. Kelvin is equal to Celsius plus 273.15. So now T1 is equal to 372.15 Kelvin and T2 is equal to 353.15 Kelvin. 2,800 meter cubed over 372.15 Kelvin is equal to V2 over 353.15 Kelvin. Solve for V2, multiply both sides by 353.15 Kelvin. 353.15 Kelvin times 2,800 cubic meters over 372.15 Kelvin is equal to V2. V2 is equal to 2,657 cubic meters. Another example: at 0 degrees Celsius, a gas occupies 22.4 liters. How hot must the gas be in Celsius to reach a volume of 25.0 liters? V1 over T1 is equal to V2 over T2. Remember, we have to convert Celsius to Kelvin. Kelvin is equal to Celsius plus 273.15. So T1 is equal to 273.15 Kelvin. Substituting in what we know, 22.4 liters over 273.15 Kelvin is equal to 25.0 liters over T2. Solve for T2. I like to cross multiply here. So 22.4 liters times T2 is equal to 273.15 Kelvin times 25.0 liters. T2 is equal to 273.15 Kelvin times 25.0 liters over 22.4 liters. T2 is equal to 304.9 Kelvin. Convert to Celsius degrees. Celsius is equal to Kelvin minus 273.15. So T2 is equal to 31.7 Celsius degrees. Next law, pressure law. Pressure law is better known as Gay-Lussac's law and compares temperature and pressure. According to the law, temperature and pressure are directly proportional. Keeping everything constant, as the temperature of a gas goes up, its temperature goes up. As the temperature goes down, its pressure goes down. If you hit a gas, the particles move faster. If the gas is in a solid container with fixed volume, this means the faster the particles move, the more times they collide with the walls of the container. That registers as increased pressure. The converse is also true. If you cool this container, the gas particles move slowly, so there will be fewer collisions with the walls of the container per second, which means lower pressure. Joseph Louis Gay-Lussac shares credit with Guillermo Amontons for formulating a gas law that describes the relationship between pressure and temperature. Gay-Lussac's law says that when the volume of a mass of a gas is constant, pressure and temperature are directly proportional. P is proportional to T. Mathematically, P is equal to KT, where P is the pressure, T is the temperature, and K is the proportionality constant. We can rearrange this equation so that it reads P over T is equal to K, or the ratio of pressure to temperature is a constant, K. The law is used to very often compare situations, a before and an after. In that case, we can say P1 over T1 is equal to K, and P2 over T2 is equal to K as well. Combining the two, we shall have P1 over T1 is equal to P2 over T2. An example. A canister of nitrogen has a pressure of 2000 psi, that is pounds per square inch, at 20 degrees Celsius. What will the pressure be if you increase the temperature to 25 degrees Celsius? Write down Gay-Lussac's law. P1 over T1 is equal to P2 over T2. Remember to convert temperature to Kelvin. Kelvin is degrees plus 273.15. So T1 is equal to 293.15 Kelvin and T2 is equal to 298.15 Kelvin. Substituting in what we know, 2000 psi over 293.15 Kelvin is equal to P2 over 298.15 Kelvin. Solve for P2, multiply either side by 298.15. P2 is equal to 2000 psi times 298.15 Kelvin over 293.15 Kelvin. P2 is equal to 2034 psi. Another example, at 10 degrees Celsius, a gas exerts 0.95 atmospheres of pressure. At what temperature in Celsius will it exert a pressure of 0.75 atmospheres? P1 over T1 is equal to P2 over T2. Convert temperature to Kelvin scale as usual by adding 273.15. So T1 is equal to 283.15 Kelvin. 0.9 atmospheres over 283.15 Kelvin is equal to 0.75 atmospheres over T2. Solve for T2. T2 is equal to 283.15 Kelvin times 0.75 atmospheres over 0.9 atmospheres. T2 is equal to 223.54 Kelvin. Are we done? No, we have to convert this temperature back to Celsius. 223.54 Kelvin minus 273.15 is equal to negative 49.6 degrees Celsius. So Gay-Lussac's law relates pressure and temperature, but we have seen other laws as well. Charles' law relates temperature and volume. Boyle's law is the relationship between pressure and volume. Combining all these three, we get the combined gas law. Notice that in order to use any of these laws, the amount of gas or the mass of the gas must be constant. The combined gas law can be stated as P1V1 over T1 is equal to P2V2 over T2. Some authors call it the equation of state, but it means the same thing. Take an example. 12 liters of nitrogen at 300 Kelvin and pressure of 1.2 Pascal is compressed to a volume of 6 liters and its pressure is 3 Pascal. What is the temperature in Celsius? Write the combined gas law or the equation of state. P1V1 over T1 is equal to P2V2 over T2. 1.2 times 12 over 300 is equal to 3 times 6 over T2. Cross multiplication. T2 times 1.2 times 12 is equal to 300 times 3 times 6. Solve for T2, we divide both sides by 1.2 times 12. T2 is equal to 375 Kelvin. This is equal to 102 degrees. Graham's law of diffusion. We have said time and time again that gases have no definite volume. The gas particles are far apart from each other and the intermolecular forces between them are usually very weak. Now this allows the gas to spread and occupy all the available space, and it explains why when a perfume bottle is opened at one corner of the room, the smell is felt all over the room after some time. Notice that in the bottle, the fumes of the perfume are in high concentration. The fumes then spread to areas of low concentration. This phenomenon is called diffusion. Defined, diffusion is a process whereby particles spread from regions of high concentration to regions of low concentration. So how fast do different gases diffuse? We look at the rate of diffusion. And we are going to start by setting up a small experiment here. So I have 2 cotton wools here. One of them I will soak in concentrated ammonia, and the other I will soak in hydrochloric acid. I will then place the 2 cotton wools at the opposite ends of a tube and then give them some time. You will notice that a ring of white fumes will form at a certain point. So why? Because concentrated ammonia solution generates ammonia gas. The concentrated hydrochloric acid, on the other hand, generates hydrogen chloride gas. The 2 gases meet and react to form a solid ammonium chloride, which are the white fumes, according to this equation. But that's not what I want us to notice. I want you to see that the point where the fumes are formed is actually not halfway through the tube. It is closer to the source of hydrogen chloride. Now, well, common sense will tell you that ammonia diffuses faster than hydrogen chloride. Actually, experiments have shown that ammonia diffuses 1.5 times faster than hydrogen chloride, and we shall see why. Now, ammonia has a molecular mass of 17 grams while hydrogen chloride has 36.5. The difference in the masses is the cause of the difference in diffusion. This observation can be summarized in the Graham's law of diffusion, which states that under the same conditions of temperature and pressure, the rate of diffusion of a gas is inversely proportional to the square root of its density. So mathematically, rate represented by R is proportional to 1 over root density D. So it means if I get rid of the proportionate sign, it means I introduce a K. So I'll have R is equal to K over root D, where K is the constant of proportionality, again fixed for one particular type of a gas and different in different gases. Now, suppose I have two gases, 1 and 2, and both are diffusing under the same conditions. R1 diffusion of gas 1 is equal to K over root D1, the density of gas 1. And I call that equation 1. R2, the rate of diffusion of gas 2, is equal to K over root D2, the density of gas 2, and I call that equation 2. Now, rearranging the two equations and making K the subject of the formula, for the first one, K is equal to R1 root D1. That is equation 3 for me. K is equal to R2 over root D2, and that's my equation 4. Now, in these two equations, 3 and 4, you will notice that K is common, and therefore it means I can equate the right hand sides of both equations. So I'll have R1 root D1 is equal to R2 root D2. Now I will divide both sides by R2 root D1. So I shall have R1 root D1 is equal to R2 root D2. Then I divide both sides by R2 root D1. Now R2 will cancel out, and again root D1 will cancel out. So I remain with R1 over R2 is equal to root D2 over root D1, or simply I can put the right hand side under the same square root sign. So I have R1 over R2 is equal to root D2 over D1, and that's my equation 5. Now equation 5 is an expression of the Graham's law of diffusion. Now, needless to say, the density is proportional to molecular mass. Now, the expression here can also be given as R1 over R2 is equal to root M2 over M1, where M represents the mass or the molecular mass. Now, the M1 and M2 are the relative molecular masses of the respective gases. So now let's bring in time. How is time and rate related? I know what you're thinking, but let's take a scenario. If a car travels at a faster speed, it takes less time. Speed is the rate of travel. Thus, a higher rate means less time. So thus, the rate is inversely proportional to time. Mathematically, R is proportional to 1 over T, and therefore we can have R is equal to K over T. Now we can therefore compare the diffusion times of two gases of equal volumes, say gas A and gas B. So we shall have K is equal to RA TA. For gas B, K is equal to RB TB. Combining the two equations, because K is common, we shall have RATA is equal to RBTB. these three equations are very important. That is the relationship between rate and density, rate and molecular mass, and rate with time. Now we can apply these equations on the diffusions we had before, that is between hydrogen chloride and ammonia, and we say Ra to represent the rate of diffusion of ammonia over Rh to represent the rate of diffusion of hydrogen chloride should be equal to Mh over Ma. So we shall have the molecular mass of hydrogen chloride 36.5 and that of ammonia is 17. So if we divide and then find the square root, we shall have 1.465. Remember, rate has no unit, it's just a ratio. Thus, ammonia diffuses approximately 1.5 times faster than hydrogen chloride. Ammonia gas is less dense than hydrogen chloride gas. Let's take a few examples. Example 1. If it takes 20 seconds for carbon 2 oxide to diffuse through a medium, how long will it take an equal volume of sulfur 4 oxide to diffuse through the same medium? What is the relative rate of diffusion? And then in the bracket there you are provided with the relative atomic masses of individual elements. Now in the solution, we first calculate the relative molecular masses of the two gases. The relative molecular mass of a compound, we will see later, is actually equal to the sum of the relative atomic masses of the constituent elements in that compound. So going by that, sulfur 4 oxide has a relative molecular mass of 64, carbon 2 oxide has 28. So from the formula, T1 over T2 is equal to root M1 over M2. Therefore, time for sulfur 4 oxide over diffusion time for carbon 2 oxide is equal to the mass of sulfur 4 oxide over the mass of carbon 2 oxide. We are looking for time for sulfur 4 oxide, so time for sulfur 4 oxide over 20, that is the time for carbon 2 oxide, is equal to 64 over 28 under the square root sign. Time for sulfur 4 oxide over 20 is equal to 8 over root 28. The square root of 64 is direct. 64 is a perfect square. Time for sulfur 4 oxide is given by 8 times 20 over root 28. We've done cross multiplication, and therefore time for sulfur 4 oxide is 30 seconds. Rates, we know R1 over R2 is equal to T2 over T1, and therefore the rate of diffusion of carbon 2 oxide over the rate of diffusion of sulfur 4 oxide is equal to time taken for diffusion by sulfur 4 oxide over that of carbon 2 oxide, which is equal to 30 over 20, giving us 1.5. And therefore, carbon 2 oxide diffuses 1.5 times faster than sulfur 4 oxide.
X-rays were discovered by Willem Conrad Röntgen. He had photographic plates which were kept in a light-tight container so that daylight could not get to these plates. These were kept in a drawer. For some reason, Röntgen actually decided to develop these plates after having played with his cathode ray tubes. Now, remembering the light from the tubes had no way of getting to the photographic plates. Yet, when he developed the plates, they were exposed. There were markings on the plates that shouldn't have been there. He had then discovered what we today call X-rays.